In a previous lecture, we had started off with some plots, saw their natural responses, namely the impulse response, the response to a step, and response to disturbance. A bit of the analysis that we carried out so far, we could now look at these plots and distinguish between, say, the transient versus the steady state. We also can largely say of how the response on the right corresponds to an underdamped system. The response on the left could simply be a first order response of a first order system. So let us check what happens to, of course, the impulse response. It goes to zero, and that's kind of nice and expected. On the other hand, the step response. So this is the signal that we would like to track. Now I see some kind of a error in this thing, right? So it doesn't really go to one, but something less than one. On the right hand side, well, the impulse kind of dies down and goes to zero, and the step response, which is the thing on the red, it goes to one. So there is on the left hand side there is an error, or now I can call it the steady state error in the step response. Now on the right hand side there is no steady state error in the step response. And I'm interested in the steady state error only because the system will take its own time to reach the steady state. After all, its transients have died down. I don't really start panicking at this point or this point or anywhere else saying that, oh, the error is too much and so on. So I'll be interested, of course, in the transients. I'm interested in what is the peak overshoot, what is the settling time, as we saw in the previous lecture, and so on. At the steady state, I will be interested only in the error. So I'll wait until the transients die down to see what my system looks like in the steady state. Okay, so why does this happen? So in a standard control block, so it consists of say a plant P producing an output Y. There is a controller C, and just keep it simple to have a unity feedback system. So there is a reference signal R of t, there is an output Y of t, and in a negative feedback setting, so this will be plus and this will be minus. Okay, so what is the transfer function now from Y to R? This will be PC over 1 plus PC. We have seen this earlier. So let us look at a case now where P is, say, of the form 1 over S plus 2. C is simply a gain of the form 5. So what is a closed loop transfer function? The closed loop transfer function, so this will be 5 over S plus 2 over 1 plus 5 over S plus 2, leading to 5 over S plus 7. Okay, let me check what happens to the impulse response. Impulse response will simply mean that Y of S is 5 over S plus 7. Let's check what happens to Y in this steady state. Y at steady state, let me call it as YSS. So this will be equal to, I just apply the final value theorem to calculate YSS is limit S going to 0, S times 5 over S plus 7, and this is equal to 0. That is what we see in the plot here also, right? The impulse response starting from in this plot on the blue goes to 0. Okay, let's take the same system and check what will be the step response. Okay, the step response. So my reference R of S will now be 1 of S, 1 over S. Y of S will be 1 over S times 5 over S plus 7. Y at steady state. I will still do the final value theorem, limit S going to 0, S times Y of S, this is 1 over S, 5 over S plus 7. So I do all the math, so this will just be 5 over 7, is something like 0.714, and whatever the rest of the decimals are. Okay, let's go back to the plot. Okay, the so if you look at this plot here, this is my steady state, right? This is actually like 0.714. Okay, now we see where the error comes from, right? So and with this kind of plot. So let me say now that I do a little modification and say that my C is now 5 over S. P remains as it is, 1 over S plus 2. The closed loop or the transfer function ys over r of s now becomes 5 over s plus 2, 1 plus 5 over s plus 2. So I compute this, this will just be like 5 over s square plus 2s plus 5. Okay, let's go to straight go to computing the step response of this, right? So the step response, so y of s is this thing times the so y of s is this thing times r of s. So r of s becomes 1 over s, again 5 over s square plus 2s plus 5. Then y at steady state will be limit s going to 0 s times the output y of s, s square plus 2s plus 5. We do the little math and we get a value of 1. Okay, that's what also my plot says, right? So I get a steady state value of 1. So in the first case, I see a steady state error here of 1 minus 0.714, whatever is the number. In the second case, I say that the steady state error, I just use the abbreviation ESS, is just 0. Okay, so the conclusion or the inference from this is that, well, there are some cases where in a closed loop system, the response to uh, reference as a step has some steady state error. In the second case, which is a second order system, the response to the steady state error did not, so the response to a unit step input did not have any steady state error. This brings us to the topic of this lecture, that is steady state error. So module 4, lecture 4, we will discuss now the concepts behind steady state error, of why in case 1 we had a steady state error of 0.228 something, and in the second case the steady state error went to 0. And where does this even show up in my block diagram? Okay, so let me just for simplicity assume that I'm just clubbing both the plant and controller into one block, and I'm calling it the G of S. Uh, Again, simplicity, I'll assume a unity feedback system, even though nothing changes with respect to the generality. So what do we want in this steady state is that Y must track the reference at the steady state. Initially, the transients will see a different responses or different curves or different values. But what I'm interested is in the steady state. So after I switch on my air conditioner, just after 5 minutes, my system goes to 24. I'm not really, of course, I'm worried that about the system going slow or fast, but I would want eventually the system to reach the steady state or 24 degrees. Similarly, if I want a car to go at 60 kilometers an hour, I set my pedal to a certain input. Does it go to 60 or does it not go to 60 in the steady state? Depending on the nature of your car, it might take faster or slower, depending, as we now know, on the time constants. Okay, so what is the steady state error? This is the error between the actual output and the desired output. Okay, this is the actual which comes out of my plant. This is the desired. This is the reference. Okay, now I can do everything by the final value theorem. I know things become easier with the Laplace transform. This is what we have done. Of course, we computed the output, but here I'm interested in computing what is the error. So this error in this block diagram comes as a result as E equal to R minus Y. What is Y? So Y over R is G over 1 plus G. Okay, and therefore Y will now be equal to G over 1 plus G times R. Okay, a couple of simple manipulations. So I have now my error is related to the reference and the transfer function via this expression E equal to R by 1 plus G. In the steady state, I'm just looking at to what is the steady state error. I'm just looking at computing this little value here. Okay, so we go next now. So what happens for a step input? So we'll just look at this particular quantity here in the red box and try to compute what happens. So for different inputs, how different system responds to different inputs and how everything really depends on what is sitting in this G of S. Again, lot of responses or everything of the system depends on the actual characteristics of the system, which is governed by the transfer function, not really of an input-output relation. It's just an internal property of a system of how it reacts to various signals. So in the first case, I have EESS will be limit S going to 0, R of S. Now what is R of S? R of S here will be 1 of S, 1 over S, S and S disappear. So what I get is something like this, where KP is limit S going to 0, G of S, and we will give it a name. And that name will be the position error constant. Similarly, now I do the same thing. So I go for a velocity input or a ramp for which, so ramp signal was what? R of t was equal to t for t greater than or equal to 0 and 0 for all t less than 0. So the plot just looks something like this. Okay, so I do again all the math. So ESS again with this formula. Okay, let's just quickly try and divide. So I have limit S going to 0. I have S here. I have 1 over S square and 1 over 1 plus G. So one S goes away. What remains is the other S. This as t goes to 0 will go to 0. And what I'm left with is just this one. Okay. And this KV, which is, again, look at it carefully, is S, the KV is limit S going to 0, S times GS, now called as the velocity error constant. Okay, now note that, okay, this is not really error in the velocity, but it's the error in the position due to a ramp input. We'll elaborate on these things a little more later. Okay, then I can keep going on one step further. If I take a parabolic input, okay, so I'll instead of now S, so the Laplace transform for a parabolic input is 1 over S cube. So one more S will show up in this, sorry, one more S will show up in the terms here. And what I will be left with is, after all the computations, ESS will be 1 over Ka. Again, I give it a name. Ka is limit s going to 0 s square gs, and the name this given to this uh, Ka is the acceleration error constants. Okay, so these error constants now largely describe the ability of a system to reduce or eliminate steady state errors. And these values depend on some kind of type of system. So what we saw here, that in one system I had a steady state error. In the other system, the steady state error was zero. We'll see a little more of why such things actually happened here. Okay, and we'll see why what this statement is. We'll just try to define a type and see as a type becomes higher, more steady state errors are eliminated. Of course, with a caveat. Okay, a steady state error is a measure of a system accuracy. So if you also look at a weighing machine, right? So you stand on top of it. Well, if your weight is 64, it goes to 64.4. You might have a steady state error, which is of say 64.4 minus 65 is zero point 0.6. Okay. In an ideal scenario, the system should match the reference input as the time progresses. It means the steady state error should be zero or as low as possible practically, if I say. It may not be in some cases totally possible to eliminate the steady state error, but we can try and design a control law which will make it as low as possible. Steady state error depends on, of course, the system itself and how is the response of the system to a certain input. So we'll see of how different uh, reference inputs, a step, ramp, or parabolic have an impact on the steady state error. And of course, I will calculate this only for systems which are closed loop stable. Otherwise, the system is just unstable, it will just deviate from where it is supposed to be, and these calculations would turn out to be not very useful. Okay, so I consider the following system. So system will have, I'll say, okay, it has a set of zeros, even though we have not really encountered a zero in any of our calculations so far, but never mind. And then I have a gain k, a set of poles, and something we will denote as the number of poles at the origin. So my setting again would be a G, a unity feedback R, a E, and a Y. And I have number of poles at the origin. Okay, so I go back here, and if I see what was happening with the G here, so here in the first case, G was equal to 5 over S plus 7. So I see what are the number of poles at the origin. Okay, so like S power n. So here there are no poles at the origin. Okay, this is okay, not so G here will be P times C. So this will be 5 over S plus 2. Sorry, not S plus 7. This was a closed loop. Okay, now I come back here. The same G, because the C was 5 over S, became 5 over S plus 2 with now one pole, this one, at the origin. And let's say, okay, 0 poles at the origin, step response had some steady state error. One pole at the origin, step response had no steady state error. Maybe I'll just write this down. The first observation, O1, if I may call, 0 poles at the origin. Okay, in this case, the step response had a steady state error. Observation 2, one pole at the origin where the step response had no steady state error. Can now say, okay, this will happen for two poles. Also, ESS will be 0, and anything more than 2, 1, 2, and anything will have a steady state error of 0. This should be a simple calculation. Okay, so system with n poles at the origin is now called a type n system. So two systems that we saw starting from the simulations were type 0, and type 1. Type 0 had a ESS and type 1 did not have a ESS for a step input. Okay, this also indicates the number of integrators, right? So the transfer function of an integrator block was just 1 over S. And as S goes to 0, this term dominates in determining the steady state error. Kind of okay, right? So type 0 system, which means no poles at the origin. Okay, we had, okay, I'll just look at the same example. G of S was 5 over S plus 2. Now I defined the term Kp. Kp was limit S going to 0, G of S. So in this case, limit S going to 0, G of S will be 5 over 2. And therefore the steady state error will be 1 over 1 plus 5 over 2. This will be 2 by 7. Okay, what was 2 by 7? It comes out to be 0 0.2, 0.28 something. Okay, so my steady state, my y at the steady state was equal to 5 by 7, was equal to 0.714 in the original plot, so which we had started off with. So here, so there was some steady state error. So this was the steady state value 0.714. 1 minus 0.7414 is the steady state error. So this is the steady state error for the same system. Okay, now because we see where we are going now. Okay, so that was it for a type 1 system, right? Where it had a steady state error. Okay, now the same system, if I look at what happens to the same system when the reference is a ramp. Okay, I still do the same. So now let's do G of S was equal to 5 over S plus 2, 5 over S plus 2. Now I'm computing this quantity called the velocity error constant. Kv is S times G of S is S 5 S plus 2. Okay, now here this will become 0. Okay, if this is 0, the steady state error, which is 1 over kV, will go to infinity. So if the reference is a ramp, then this error will go to infinity, which means a type 0 system will never be able to track a velocity input and therefore also an acceleration input. Okay. So what can a type 0, sorry, we're talking of type 0 systems, right? A type 0 system, between this right here, type 0 system can track a step with some error, and similarly a type 0 system can not track a ramp, which is 1 over s square. It cannot track also a parabola, 1 over s cube, or in anything higher than this, 1 over s4 and so on. It will never be able to track. So if I am tracking, say, this signal, my so this is uh, uh, my ramp signal, this is my R, and maybe my system will just be something like this. And you see, as time goes, so this is my reference R of s. Maybe this is something like my Y of s. And as time goes, the error just keeps increasing. It doesn't seem to be converging to anything. Okay, this will be true for RAM, this will be true for parabola, and so on. Okay, now things will slightly be better when I look at a type 1 system, where instead of C, I had a 5, C was equal to 5 earlier, I had a 5 over S, the plant was S plus 2. Now this is my G of S now, which was like just the loop transfer function, the forward loop P times C. It has one pole at the origin. Okay, now what is Kp? Kp is limit S going to 0. Let's recall the definition. Kp was equal to limit S going to 0, G of S. Okay, limit S going to 0, G of S. So this will be, sorry, oops. Okay, this will be 5 over S, S plus 2, which means Kp will now be infinity because of the S in the denominator. If Kp is infinity, steady state error is 0. That's what we saw in the second example here, right? So this had a pole at the origin, this one, and the steady state error was 0. So the observation here is that a type 1 system will track a step. A type 1 system will track a step reference with 0 steady state error. Now I look at the same system and look at what happens to the velocity input. I am now looking at this one. 1 over S G times S. So this will be, sorry, I'm looking at KV. The velocity error constant is limit S going to 0, S times G of S. So G of S will now be 1 over S, S plus 2. This is a 5 also here, right? This S and S will cancel. So here I will have a number which is like 5 over 2. Okay, this is a finite number, right? And therefore the ESS for velocity will be 1 over this number. So type 1 system will track a velocity input with a finite error. Okay, so this is summary. A 0 position error, a constant velocity error. If I go one step further, I do the same analysis, I get an infinite acceleration error at steady state. Okay, this is fine. Now I go to type 2 systems. The same analysis will follow. For type 2 systems, again I take the same G of S, the position error. So as I saw, if I had add more integrators, if I have instead of 1 over S, I have a 1 over S square. Okay, it will track a step, it will track a ramp, and it will track a parabola with a constant steady state error. So if I just then go to type 3 system, 1 over s cube and something, then this also will become 0. So as the number of poles increases, the ability to track higher order signals will also increase. Okay, and then we can just do the same analysis that we do. So in summary of this week, we started off by talking of time response specifications. We classified what was the natural and forced response. We saw a lot of simulations of the inverted pendulum, the normal pendulum. We also saw transient and steady state responses with several examples. Then we started off looking at response of first order systems. Then uh, we introduced or we studied the role of the time constants and how fast or slow the system responds to different time constants. Second order systems, which had a wide variety of examples from circuits to mechanical engineering to buildings to even biomedical applications, presented us a much more wider perspective in terms of its damping ratio. Systems could be underdamped, overdamped, critically damped, undamped. And this also, the special case of underdamped, also gave rise to some more terms like the peak overshoot and the settling time, giving a little more excitement to the analysis of transient behavior. So the lower the damping, faster was the response and more was the error. So in summary, we conclude we had a wide variety of discussion now on what happens when I switch on the system till it reaches its final value. How the transients behave, how fast, how slow, is there an overshoot, is there not an error shoot, or is there not an overshoot, how fast, how slow it settles, everything depending on the zeta and omega n, which are the properties of systems. And after all the transients are over, we also checked what really happens at the steady state in terms of steady state errors and the ability of integrators to overcome this stability, these steady state errors. Next time when we meet, we will go further and see how to use this analysis to design controllers to perform certain tasks. That's coming shortly. Stay tuned. Thanks for watching.